All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another, the first edition of Math 1206, Calculus 1. I hope you all are doing well. Let me make sure. Okay. All right. Awesome. Thank you for turning your cameras on so I can see you guys. Nice to meet you. So I will be your instructor for this month. That's going to go by like that. Seriously, like every class, every day is going to be like a week. So normally this class, Calc 1, is like a 3 hours per week class. So yeah, it's going to go by blazing fast. So hopefully you guys are ready. It's very doable, but it's also not something you want to slack off on. Just forget about having weekends. Like you don't have weekends for the next month. Just forget about it. So what we're going to do today is I want to talk to you about the class, how it's going to be run, make sure that we're all on the same page. Still have a couple people missing, but hopefully they'll turn up soon. And let's begin. So hopefully you guys are seeing my screen. Okay, so this is the syllabus. And in case you're wondering where you can get that, I am going to paste the class webpage in the chat box. Okay, so you can click on that. In fact, maybe I should actually show you that. The link I just gave you will bring you here, which is going to be our main website. And it's probably the first thing I want to tell you guys about. So this is the website for the class. Okay, so lots of stuff is going to be here, and you can actually access everything from this hub right here. So I have a few sections of the text just in case you want to get it, but we'll talk about that. You'll all have access to the text. I will be recording the lecture, and you can access the lecture videos there. The syllabus, which I'm going to read through with you guys, can be here. If you click on it, you'll get to that same document that I'm reading through. We're going to have online homework. These are the instructions, and this is the code that you will need. Your grades are going to be stored here. You'll go there for your report. You can ask questions here, and you will take tests here by clicking on this link. So each of these guys, they're hyperlinked to the websites that you'll need. So we're going to be doing tests on a website called Gradescope, and your grades are going to be on a website that looks like this, Jupyter. No, what's going on there? And yeah, so you have that link. We won't be doing quizzes because there's just like no time. If I were to give you guys quizzes at the same time, it would be a nightmare. But I posted some old quizzes from a semester-long class, so you can use those to help you practice. Reviews for your tests, they're already up here. So you can see the test 1 review there. You can see solutions here. I gave you instructions on how to use it. This is a previous test 1 that I gave, I think spring 2019. Then you have the same thing for test 2. You also have some mock finals up, and you have some documents that will be useful later on. So this class, the class webpage is really useful for a bunch of stuff. So you should actually know that. You can actually go to jhevon.org/teaching, and that would bring you to this page, which you can just click on your class right there, summer 2021. That brings you here, where you can find the syllabus and everything. All right, awesome. So now that we know how to find the syllabus, let's actually go and talk about the class. My name is Jhevon. Nice to meet you all. Hopefully you're all doing well. We're in for a long one, 3 hours all at once. We'll try to take a break in between, maybe 5-10 minutes, maybe 15, depending on what's going on. But yeah, try to stay awake, and hopefully we can get through this. So as you see, that's my name, Jhevon, and that is my email. And I know what some of you are thinking. And in fact, yes, it's true. I am the 306th J. Smith at Fordham. And those are my office hours. And I just put that to put something down. Really, it's kind of flexible. Particularly on Mondays and Wednesdays, I would usually have times that I can meet with everyone. Tuesdays and Thursdays are kind of tricky, but I just put down Friday just because. Office hours will be held over Zoom. So if you email me and say, hey, I want to see you during office hours, I'll send you a link and we can discuss a time that's mutually convenient. So there's the class website, the class web page. I linked you to that. This is the text we will be using, but by signing up for the online homework, you will actually have access to the test. And yeah, usual syllabus stuff. The usual boilerplate. You have the disclaimer here. Someone's trickling in. Talk about the websites. There's the course description. So it's calculus, and we'll be studying these things. Calculators are in general not allowed, for whatever that's worth. But I will expect you guys to be able to work things out by hand overall. Usual, typical GPA chart here. Fordham doesn't have an A+ grade, so the highest is going to be A's. But that's just kind of a guide. Overall, especially in the summer, I'll kind of be grading on a curve, so it'll be a little bit more generous than this, but that's the standard one. And how things are going to be broken down is the following. So homework, tests, and final. That's how it's going to be. That's what your grade is going to be. If it was a longer semester, I would also give quizzes and all that, some other stuff. But for us, this is it. So we have online homework. We have 2 tests. They're not cumulative. And again, it's a month-long class, which means like test 1 is like 2 weeks from now. And then test 2 is like 2 weeks after that. And then the final is going to be a few days after that. So it's going to go by really quickly. So we have 2 tests. They're not cumulative. So each is worth 25%. Your homework is worth 15%, and the final is worth 35%. And I'll talk more about each of these as we go on. Makeups, you have to have a good reason, as usual. Attendance, I'll be checking attendance during the first 2 classes because I have to make sure that you guys, whoever registered, is actually showing up. So on the break, when I go for a break, I'll actually take attendance to see who's actually here to make sure that who's here is supposed to be here. We'll talk a little bit more about that. But yeah, overall, usually during the semester, during in-person classes, I would even give a little bit of percentages for attendance, but I mean, it's online class now, so not really. Work ethic. Don't slack off, especially in a summer class. Like I normally put this in my syllabus, but it's like quadruple true for you guys. You are doing 3.5 months worth of stuff in like less than a month. So you need to really be on, you can't slack off. Is there anyone who's taken calculus before? Anyone has experience with calculus? Okay, so let's see, one person. Okay. All right. So whether or not you have experience with calculus, I know that If you had experience with it in college, that's one story. But I do find that students who have experience with calculus from high school tend not to do so well, because high school calculus and college calculus, they kind of expect different things from you. So whether or not you've seen calculus before, yeah, you have to work hard. Give it 100%, 110%. I don't think you have to have seen calculus before to do well. In fact, if you're very good at algebra, I think you would do fine. In fact, the reason why people fail calculus is because of algebra, right? So a lot of people would think that calculus is the difficult thing. It's not, right? It's algebra, right? People fail calculus because of algebra. You'll realize that the calculus part is actually quite easy. And it's just like you figuring out how to simplify something or solve an equation. That's where people always mess up. So yeah, don't slack off. Work really hard, starting day one, starting tonight. Yeah. Okay, so homework and test. As I said, you can click on the website to find the homework. You're going to need this code to sign up. I believe all the homework for chapter 1 is already posted. And the due dates for the homework, I set it to be the end of the semester. So I think it's due around, I want to say June 30th. So I wanted to give you guys some flexibility, but at the same time, don't wait until June 30th to do all the homework. Do the homework as we go along, right? But I'm going to set all the homeworks to be due on like the end of the month. But you want to do them, and especially before the test. So test 1 is going to cover up to like chapter 3. So you at least want to make sure that you do all the homeworks for up to chapter 3 before test 1 hits. So you definitely don't want to save it all for the end. As far as homework goes, there's no makeup, and pretty much if you have minor technical issues, I'm going to ignore them because it's going to happen. It's online homework. So to make up for that, what I would do is if you get an 85% average overall on homework, I'll just bump it up to 100%. So you can miss 15% of the homework or have technical difficulties for 15% or forget to do 15%, and you'll still be fine as long as you do well on the other 85%. And you have unlimited attempts, which I think in grades in WebAssign, it just really means 100 attempts. Usually students don't need more than 100 attempts to get a question correct. But yeah, so that is homework. It's going to be online through WebAssign. So it's not free. So just so you know that. But you do get a 2-week trial period. So I don't know if you want to study ahead and just like time it so like you can cover everything in like 2 weeks. I would be fine with that. But overall, after the 2-week trial period, you're going to have to pay to continue. It's just that the free sources of online homework, they're just not as great, and not, I don't have as much variety. So WebAssign has been used a lot. And if you pay for unlimited, it will actually carry you through the fall semester as well. So if you know ahead of time some of your classes are going to be using WebAssign, you can get it now and you don't have to pay for anything, any new classes in the fall if you get the unlimited, which isn't too much more expensive. Okay, tests will be on a website called Gradescope. I briefly showed you that. You guys should have seen emails from this. And pretty much you're going to have the questions there. You're going to have to scan your work and upload it. And by scanning, what I really mean is you can literally take a picture on your phone and upload it to Gradescope. So you'll be able to log into Gradescope on your phone, and you can like take a picture of your work and upload it directly from your phone. So it shouldn't take you a long time to do it, even though I will be giving you a few minutes to upload. So maybe 15 minutes extra than I would normally give for uploading purposes. You will be able to log into Gradescope from several locations. So, but the first login is the one that will submit the work. So you want to submit from your phone. So I would say log into Gradescope in your phone first. And then if you want a bigger screen to like read the test off of, you can log in on your laptop after. So you can read from that, do your work, and then just take a picture and upload it directly from your phone. Shouldn't take long, especially if you make the resolution. It doesn't have to be perfect resolution as long as it's readable. Do some tests, make sure that you can read from your scans, and make sure that I can read. Yeah. And so you can upload stuff while you're working on the next problem. It shouldn't actually take you too long if you do it correctly. Last semester, I had students going through all these little things. Well, I have to transfer the scans to my laptop and print it out and rescan it. And I'm like, dude, you have a smartphone. Just log in on your smartphone, take a picture. It's not that big a deal. Okay, the final exam, as I mentioned, the tests aren't cumulative unless where it's incidental, right? So there are times where you learn something for test 1 where that technique carries over to test 2. So there's going to be overlap in that sense, but I'm not going to directly test you on test 1 material on test 2. They're kind of separate. We'll talk about that a little bit more. The final, however, is cumulative. The final is essentially going to be like test 1 and 2 mashed together, pretty much. So test 1 and 2, they're going to be an hour and change long, and the final will be 2 hours and change long. Yeah. Okay, so I give some advice here about what to expect to understand that different aspects of the class are meant to test you at different levels. So not everything is going to be exactly the same, and that is by design. So I know there's this running joke where students are always like, yeah, this is what we learned in class, and this is what it gives us on the test. You know, like in class, 1 + 1 equals 2, and then on the test, like calculate the distance to the sun. Right? You guys know the meme. So it's going to be, you're going to be prepared for the test, but just understand homework is probably going to test you starting at the basic level, building up, and your test is going to assume that you're an expert. And so you don't want to think of those as the same. But you will have mock tests. You will see old tests that I give. You'll know what level I'm testing you at. You'll know what to expect. Nothing should be a surprise at the end of the day. So I just want you to know that. Now, when it comes to online classes, which you probably have experience with since we've been in lockdown for over a year, when it comes to mathematics, I don't think that you have to have a lower quality experience than you would in person. I mean, yes, if you're like an extrovert and you like being around people, there's going to be that, but I don't know, you have to find someone else to hang out with. I don't know. But in terms of your ability to learn the material and get good at it, I don't think the online situation is going to really hurt you, provided that you do certain things. So when it comes to online classes, one of the major problems is that it's so easy to disengage to the point where you're not even going to realize that you're disengaging sometimes. Because when you're in person and you're in class, you know, you have an entire room of people all looking in the same direction at that weird guy at the board, right? There's like an environmental reinforcement that, oh, I should be paying attention to over there. Whereas at your house, it's not going to be like that, right? There's going to be, you know, your cat or your little brother's running around. Like there'll be distractions, and it's going to be easy to get distracted or just notice random stuff. So what I would say to make sure that you have a good experience with an online class is to actually engage in the class, right? So there are times when I'll ask questions, try to answer. Even if you don't know the answer, it's okay. I don't expect you to know everything. when you're learning something for the first times, I expect you to make mistakes. I don't expect you to be perfect. It's okay. And if you say the wrong thing, I'll correct you. And you want to say the wrong thing so that I can correct you before the test comes around. So whether or not you think you know what's going on, just do a guess, right? Talk, engage. It turns out that actually the more you talk about math is the better you'll actually get at it, which I guess I'll talk a little bit more about that as time goes on. But yeah, engage. That's a big thing. So you want to talk in an online class more than you would in an in-person class. And that kind of overcomes that issue of you kind of disengaging. So participate, answer questions, ask me questions, respond when I ask questions, and all that stuff. Okay. Yes. So you can ask questions on a forum that I created for you guys. You can post questions anonymously if you want. And so you might even have your classmates answering questions if they know, which was good practice for you. So I like the forum idea as opposed to people sending me questions in email and then maybe it gets lost or something, because I get so many emails now. So you can ask questions on a forum. I'll see them. I'll be able to respond to them. If your classmate happens to be up at that time, they might be able to know the answer and say, oh, I think this is the answer. And then I'll be able to endorse answers and all that good stuff. So that's great. Next section, prerequisites. So I expect you to remember all the math that you've ever done before this. Well, mostly in line with algebra and pre-calculus. So if you've done algebra, I expect you to remember everything from algebra class. And it's very important. So I'm not going to be able to go over that stuff with you, which maybe I'll. Yeah. So if you go back to the main website, jhevon.org/teaching, right, in fall 2020, I taught pre-calculus. And you can see practice problems there, quizzes there that you can try if you want to look over a topic, as well as if you want to see all the lectures, you can. So I don't know if it's the most efficient thing to watch a whole lecture video as opposed to just reading. But if you're the kind of person who likes watching videos, you do have the option to review your pre-calculus. If you go through this course, making sure that you know everything, you'll be in good shape for this class. More specifically, I guess I can say, what do I expect you to know? So things I expect you to know about, right? So I do expect you to remember things like functions, what a function is, what's the definition, notations like f of x, properties of functions like domain, range, when a function would work from when it doesn't work, how rational functions behave, radical functions behave, polynomials. I expect you to remember the different types of functions. So you have polynomial functions, rational functions, radical functions, exponential, logs, trigonometry, and algebraic, which is kind of just like a mishmash of all of them. I do expect you to know basic graphs, like how to graph basic functions. I expect you to know a bunch of graphs by heart. So like y equals x, y equals x squared, y equals x cubed, y equals radical x, absolute value of x, all these things that you see here. I expect you to be able to graph those quickly from like memory, like you shouldn't even have to do any calculations for it. By the way, the notes here, before I forget. Did I post a link? I know I created a link. I don't remember if I posted it. I will give you access to these notes, so you don't have to write everything, but make sure you jot down the important things as we're going along. So I mean, this you don't really have to write down at the moment. But if I'm going through examples or I'm talking about certain concepts, I would encourage you to write just to be engaged. But you will have access to all my notes. And I will also put a link to the notes on the video, in the video description. and I'll put a link to the lecture notes on the class webpage. I thought I did that, but I think I forgot. Yeah, so note to self, I'll put a link to the class notes on the class webpage as well. So you'd be able to see this, and you'll be able to even see it in real time. So it's a direct link to my OneNote notebook. So yeah. I do also expect you to know how to graph basic things. Like if I gave you the equation of a random line, you should know how to graph it. If I gave you the equation of a random parabola, you should know how to graph it. So if I ask you to graph x squared plus 5x plus y equals x squared plus 5x plus 6, I expect you to know how to graph that. I also expect you to have certain algebra skills. This is actually where people mess up a lot. So I do want you to take some time to make sure you go over everything. Make sure you know how to simplify stuff, know how to manipulate stuff, know how to factor different things, know how to solve equations, specifically quadratic equations, but also other kinds of equations. Know how to operate on functions, add two functions together, subtract functions from each other, multiply them, divide them. Take compositions like f of g of x. Expect you to know that. I also expect you to know about trig functions, just the basics at this point. So just know what sine, cosine, and tangent look like. Know what their values are at special angles. For example, you should know that sine of pi over 6 is a half, and sine of pi over 3 is radical 3 over 2, etc. Cosine of pi over 4 is radical 2 over 2. Things like that I expect you to remember. All of that I went over in the pre-calc class, and I have mnemonics for all that. So if you want to brush up on trig, you can do that. We're not going to do tons of work with the other trig functions like secant, cosecant, and cotangent, but you should know what they are. You might see them in the homework, but in practice, I'm not going to test you a lot on them. I might do a little bit of work with secant, but overall, if you really understand sine, cosine, and tangent, you should be fine. Okay, so those are just some basic things I expect you to know. Know about functions, graphs, have your algebra skills in order, know about trig functions, know how to solve equations, graph stuff, manipulate, simplify, etc. And we'll be doing a lot of practice with that today, in fact. All right, this brings us to the next section. Blasphemies, which I admit is a very inflammatory word, but I'm going to stick with it because I do want you to think of these things as inflammatory. Very, very important. Do not do this stuff. So I want to talk about that for a little bit, because if you make one of these mistakes, I'm going to punish you very heavily for it. So I want you to know what these guys are. So let's actually talk about these. So there are some things that from now on you should just never do. Just don't do it, no matter what. And it turns out a lot of times knowing what not to do is actually very helpful, just as helpful as knowing what to do. Because usually when you are in a situation where you're like, I'm not allowed to do that, then what you have to do becomes obvious because there's not that many things you can do. So let's talk about that, right? Mistakes you must never make, ever, no matter what, under any circumstances. Okay, so let's talk about that. So 1, do not cancel cross sums. Okay. Now these guys you should be writing down because you don't want to make those mistakes. And they're very sneaky because they'll sneak up on you a lot of times. A lot of times students will know better, but when they're working on a huge problem and there's like this, they make that mistake in this one little spot right here that messes everything up. So these are very common mistakes, and I'll talk about, probably not today, why they're common, But just know that you shouldn't do these things. So let's make sure you know what that means. Yes?
Well, I don't know if it's showing on your screen, but on mine it says this this meeting is being recorded, so it's kind of blocking your sentence.
Come again?
So on my computer, it says that this meeting is being recorded. I think it's on your computer, but
oh, there's nothing on my screen.
I think it's mine.
Yeah. It shouldn't be blocking anything, I don't think.
I fixed it.
Because I'm seeing what you're seeing on this screen, and on my screen, I don't see anything on either one.
It was my computer. I'm so sorry.
Okay. All right. No problem. Yeah. Anyone else have any issues? Let me know. So let's actually talk about this first. So what do I mean by don't cancel across sums? Well, something like this. Let's say you're working out a problem. You did tons of steps, and you got to this point where you're like, okay, 2x plus 1 all over 2. And you're like, I can cancel the 2's. And does it give me x plus 1? You cannot do that. Very, very wrong. You do that, Jhevon kills you, okay? Kill you, right? You cannot do that. This is called canceling across the sum. You cannot cancel when there's a plus or a minus sign in between terms. It's not allowed, right? You can only cancel across multiplication and division. Right? So this you can do. So what does that mean? If you had like 2 times x plus 1 all over 2, then you could cancel the 2's and you would get x plus, and you would get x plus 1, and that is fine, right? And that's fine because it's multiplying, whereas up here, it wasn't multiplying. The x and the 1 were separate, right? So you can think of like addition and subtraction as separating operations, and multiplication and division as like combining operations. And you can only cancel across multiplication and division. You cannot cancel across sums, okay? So if you have something plus something all over something, you can't cancel that thing into one of the thingies. That's very bad, very wrong. Can't do it. You can only cancel when you have multiplication. So yeah, so that's canceling across sums. Very common mistake, but it shouldn't be, really. Just know that you can only cancel across multiplication and division. So don't cancel anything unless you have multiplication and division. If you don't have multiplication and division, you can do something like factoring. So for example, you may need to factor. So let's say I had 2x plus 4 all over 2. What I could do is I can factor out a common 2. And now I've created a multiplication where there was none, right? So now I wrote it as a multiplication, right? Which is what factoring is. Factoring is taking a sum and turning it into a multiplication, right? And so that I can say x plus 2 is the answer, and that would be fine. But you cannot cancel. So if you were to do like this and that, bad. No, can't do it. So you can only cancel across multiplication and division. Okay, so that's the first thing. Don't cancel across sums. Never. Okay. Second thing. Let me make sure that... and this one is even sneakier sometimes. Do not distribute powers across sums. Okay, what do I mean by that? So let's say you had x plus 3 all squared, and someone goes, oh, I know what I can do. I can just square the x, square the 3, So that's x squared plus 9. It's not x squared plus 9. That is called distributing powers across sums. It's like you take the square and you distribute it across a sum. That is wrong, very wrong. You cannot do that. Okay. You can distribute again across multiplication and division. Which we'll talk about. So for example, if I had like 3x all squared, where there's a multiplication here, I am allowed to square each term. So that's 3 squared times x squared. That is 9x squared. And that is allowed because it's multiplication. You cannot do it when there is an addition or a subtraction, right? So you can't do it whenever it's separated. I already did addition. Let me actually turn this into a minus sign. See, I don't want you to think of a sum as adding. A sum can be a subtraction as well, right? Sum just means addition or subtraction. Okay. What is that though? So I know what's not the answer. What is the answer? Yeah, no, go. Just jump in.
Well, you factor it out or you expanding, you get x squared minus 6x plus 9.
Yeah. Now, there are a couple ways that you can get to that. One, you just realize that this is just that thing multiplied by itself. And we have this thing called the distributive law. So you can take x and multiply out, and then you take the 3 and multiply out. So you would get x squared minus 3x plus 9, and then you get x squared minus 6x plus 9, right? Or what you want to do is use the formula. So you should know that a plus b all squared is a squared plus 2ab plus b squared. And if you throw a minus in there, it just changes the middle sign. And so it's the, so when you have x minus 3 all squared, you square the first term, multiply both terms and multiply that by 2, right? So you take x times minus 3 times 2, that gives you minus 6. And then you square the last term, which is 9. And so you can do that way, right? So this is not wrong, but this is the rookie way to do it. We don't do it that way anymore, right? Not that it's wrong, but the thing is, when we're at this level now, we're going to be doing a lot of things all at once. So you don't really want to take a long time to do basic things. You really want to be able to do things quickly. So whenever you have a basic formula, like you should know like your difference of squares, your difference of cubes, your sum of cubes, your squaring a binomial, things of that sort. You should just know this is the way we do it now. Okay. You want to start to think in terms of principles, in terms of general rules, and that will actually give you, set you up very well for the rest of the class. Because at the end of the day, I'm going to be giving you a lot of rules, and you're going to need to know how to apply them to certain things. You're going to want to know how to use these rules as templates. And so you really want to go over your algebra and your pre-calculus in terms of applying rules as opposed to like just brute forcing through everything. So I recommend that you know how to apply formulas as opposed to just doing everything bare bones and basic. Yeah. Here's another way that distributing powers across sums can get you in trouble. Sometimes we see something like this. And we're like, oh, I can do this and that. So that's just x plus 2. Not x plus 2. Why is it not x plus 2? Remember, radicals are powers, right? Whenever you see a radical, it's really a power. It's just that it's a fractional power that's not a whole number. That's how you get a radical, right? So when you see this, what is that? If I were to write the radical as a power. Yeah, go.
It's x squared plus 4 to the 1/2 power.
Right. This really means 1/2 power, which means doing this and just putting the half power in each, not allowed. But students do that all the time. They see a radical of a sum and they just decide to, oh, just take radical of each individual piece. Not allowed. It's not right. In fact, when you go to Calculus 2, you'll realize that to actually write this out as a sum of things, you'll actually need an infinite number of terms, right? So it's not like here where, oh, I just missed the middle term. It's like, no, if you just do this, you're missing an infinite number of terms. To expand a radical as a sum, it's actually pretty hard. So you're not allowed to do that. Again, you can across radicals across multiplication. So, for example, if I were to do, instead of my x and 4 being added together, what if they were multiplying each other? Like this. Okay. Then that you can actually do this. Right? That's actually allowed. Now, let's see how much we remember from the previous class. Technically, what I just wrote down is incorrect. Can anyone tell me what, how to correct the mistake? Do you see what the mistake is? It's not the distribution of the radical, so that's a hint. Yeah, Nicole?
Sorry. It has to be plus or minus, because you don't know if it was like a positive number or a negative number.
I know what you're thinking, but no. Plus or minus comes when you have an equation where one side is squared and then you take the square root of both sides in order to simplify it. That's where a plus or minus comes from. It's not going to be here. Here I already have the positive radical. So that's not the issue. Right? Like if you have a radical 4, we just think of that as positive 2. You don't think of it as plus or minus 2. But if you had x squared equals 4 and you take the radical of both sides, then you put the plus or minus. So it depends on if the radical was there in the beginning or not. Usually when we write the radical, we mean the positive radical.
Professor, what was the question?
There's a mistake in this line. I want to know what it is.
I have an idea, but I'm not too sure if it's correct.
Okay, sure.
Would it be so where you have 4x squared equals the square root of 4 multiplied by the square root of x squared? Would it be like the values underneath the square root?
What do you mean, the values under the square root?
It'd be like the correct answer or correct would it be the square root of 2x multiplied by the square root of 2x? Or not, maybe.
You mean like if I wrote this as 2x times 2x?
No, like you break it up. So the square root of 2x and then multiplied by the square root of 2x.
Okay.
Would that be it? No. Okay.
That doesn't really make it simpler, I don't think.
Okay.
Because you could still break that down further. And then you can multiply these two and get 2. And then you can multiply these two and get your square root of x squared. Right, so you can still make that nicer.
Okay. So is it the answer then?
It's not the answer. Here's a hint. If I were to take the square root of 2 squared.
Is it that you have the square root underneath the form of the sign? Is it that?
No, not exactly. But what is this? The square root of 2 squared. What would the answer be?
It would be the answer itself. Like, because 2 squared is 4 and the square root of 4 is 2.
Right. They kind of just cancel. What if I ask you, if I put a minus 2 instead, what would happen?
It would be the same thing because
You would get the same thing. That's a hint. What is the correct answer?
So
notice that you don't just get x, right?
Oh, so
because if this here, my x is minus 2, this is not x, right? And so I'm not allowed to write x here. It's x in this situation.
Oh.
But it's not x in this situation.
It would be plus or minus? No?
Not exactly. That was already suggested. What else reminds you of this? Right, I put in a positive 2 and I get a positive 2. If I put in a negative 2, I get a positive 2. What does that remind you of?
Repeat that for me.
What does this remind you of? If I put in a positive 2, I get a positive 2 out. If I put in a negative 2, I get a positive 2 again.
Is it the cumulative law? So like negative times positive equals negative. Negative times negative is positive?
Right, but I'm saying if I were to plug it, like this same thing would happen with like 3, right?
Mm-hmm.
Whether I plug in a positive or a negative, it gives me the positive answer. What does that remind you of? Afwan, go.
A parabola?
No, a mathematical operation, not a graph. It doesn't have to be a parabola, right? Like I could do... That would still work. Okay, I don't know if you're going to kick yourself when I actually say what it is. But you guys are kind of skipping around it. Absolute value, right? Absolute value always turns things positive, right? So remember, absolute value of x, it's a piecewise function. It just gives you the same output if your output is positive, and it changes the sign if the output is negative. If the output is 0, it just gives you 0. So if I take the absolute value of 2, you just get 2. If I take the absolute value of minus 2, you get 2. Right? If I take the absolute value of 3, you get 3. If I take the absolute value of minus 3, you get 3. Take the absolute value of 0, you get 0. Right? So this is the absolute value function. You should remember that it looks like a V. So pretty much, if I have a 2, it outputs a 2. And if I have a minus 2, it also outputs a 2. Right? That's what the absolute value function does. So it's actually, you need an absolute value here. The only way that you would be correct to not have the absolute value is if we had the square root of 4x squared and we know x is positive, then you'd be able to say this. Technically it's this, but remember, when your thing is positive, the absolute value just gives you the original back. Right? When your x is positive, absolute value is the same as x. Right? So the absolute value x here is the same as x. So that's the absolute value function. It's a very important function. We're going to use it in a lot of counterexamples, so you need to remember it. How it behaves, what its picture looks like. Yeah. So whenever you take the even root of something to an even power, an absolute value is going to happen. Because what happens is when you take the even power, it turns all negatives to positive. So even when you plug in negative answers, you're going to get a positive outcome. And you can get that by thinking absolute values. Okay.
So
Third thing.
You do the radical of something, or like you write down the solution, for example, you have to include the absolute value symbol to like.
Yeah. If I did not tell you this, you need the absolute value. It would be incorrect without it.
Okay, got it.
Right? Because as I showed here, if I were to plug in, so if I had, say, 4 times minus 2 squared, what would the answer be? It would actually be 2 times 2. It would give you positive 4, right? It wouldn't give you negative 4, right? The negative would turn into a positive. And that's what the absolute value does. So little things like that we need to remember. But let's move on. 3. Don't divide by 0.
I have one more question on the
Yes.
radical thing. If it was x cubed under the radical, would you not have to worry about it since
That is correct. So if you have the cube root of x cubed, it's just x. It will keep the sign, right? And you can see this because if you take the cube root of, say, 3 cubed, obviously you get 3. But if you take the cube root of negative 3 cubed, you would actually get negative 3, right? Because when you cube the negative 3, it stays negative because you're raising it to an odd power. And then you take the cube root of a negative, it just stays negative. So it actually follows the sign. So you can do that as a general rule if you want. We should know that this is equal to absolute value of x if x is positive. It's equal to 0 if x is 0. And it's just equal to x if x is negative. So you could have that rule. It's based on the even. if n is even, right? Because that means the even n is going to make any negatives turn to positives. So you can capture that with an absolute value. And if n is odd, that would be the definition. And it's 0 whenever you're doing it with 0. Speaking of,
can you please just go back to like up a little bit more? There's something I want to copy down. Yeah, that one. Okay. All right, all good. Thank you.
okay. Third thing, and this is going to be very relevant. You probably didn't come up with against this a lot in pre-calc and algebra, but we're going to come up with it a lot in this class. Do not divide by 0. It's meaningless. Okay, so if you write down something like 2 divided by 0, and you tell me that that's infinity, or oh, that's 0, or whatever, I'm just going to mark everything wrong and move on with my life. This is meaningless. It's not infinity, it's not negative, it's not anything. It's like, it's gibberish, right? It does not make sense to divide by 0. Okay, now we will see similar things, such as there are times when I would write 0 with a little positive here, and that you can interpret as infinity. Or I would write 0 with a little negative here, and that can be interpreted as negative infinity. Because when you write 0 with that little symbol, plus or minus, what it means is it's not really 0. It's slightly positive, but it's super close to 0, right? And that can mean something. But 0 itself, you can't actually do it. And you can just think of a function like 1 over x, right? When x is 0, there is no output that fits that, right? Your x cannot be 0. Like there's nothing here. There's no output there, right? 0 cannot be in the denominator, right? So that's something that you learned in pre-calc as well. Don't divide by 0. It's never the right answer. Never write it down. But we'll look at we'll talk more about this later. When we study a topic called limits. Okay, but division by 0, no. 4. Now 4, this is more of a do as opposed to do not. Do use parentheses. This also goes with proper notation. There are times when, was I underlining these things? I don't think it was. There are times when students get lazy and they decide not to write certain things down. Okay, we're running out of, gonna need a lot more space here. So they may even know that they should be using parentheses, but they don't. They decide not to write it for some reason. I don't know why. Maybe it's just don't do it. Notation is very, very important. It can tell you a lot just by paying attention to notation. So sometimes it might seem to you that it's very cumbersome to write, but it's actually a guide. And being sloppy with notation will come back to bite you eventually. So sometimes students will know in their head, oh yeah, I'm supposed to have a parentheses here, but they don't write it down for whatever reason. So they know in their head up here that there's a parentheses, but they're working on a long problem. By the time they get 9 steps deep, what do you think is going to happen? They're going to forget about the parentheses. I see it all the time, right? Especially if you're in like a test and you're like freaking out, right? Like I know in my head that there's a parentheses here. And then Jhevon is like, 5 minutes left. Oh, and you start rushing. Now oh yeah, now that you forgot about the parentheses, didn't you? Write it down. It's not a big deal to just do that. Just do it, right? Just do it. Write the parentheses down. It'll save you so much headache. I know a lot of students who just think, well, yeah, I know it's supposed to be there. Like students say that all the time. I know that if you know it, do it, write it down. It's not worth it. It's not worth the half a second it takes to do that, right? You're going to make a mistake at some point. Just write it down. So to kind of illustrate this, I want us to work through a little bit of a longer problem. And this is going to flex our pre-calculus and algebra muscles. So let's do that. Okay, so here's what I want us to do. Let f of x equals, let's say I'm doing 2 minus x. 2 minus x squared. Okay. And then I ask you to find, or not find, let me say compute and simplify f of x plus h minus f of x all over h. Now that expression should look familiar to you. Does anyone know what this is called? F of x plus h minus f of x over h. What is this guy called? You can go.
Is it the derivative of a function?
No.
I've seen it in calculus before. Rate of
Yeah.
change.
Yeah. But no, you would need this in front of it to be a derivative. As written, it's not a derivative. Remember what it's called? It's called the difference quotient. It's certainly related to the derivative, but the derivative is a refinement of this expression. It's a very important expression in calculus. Some of you might recall seeing it in algebra and pre-calc, and you may have even wondered, like, why are they asking me to find this random thing? Like, why would I even want to do this? In this class, you're going to learn why you would want to do this. But for whatever reason, let's say we actually want to do this. How do we actually go about it? Let's see. Okay, so if that's my f of x, what is f of x plus h? So tell me what to write here. Someone can just talk it out. Let me.
So you're asking about the first portion of the equation.
Yeah, f of x plus h, what is that?
Would it be f times x, so fx plus f times h? No.
No. So this is a function, right? So this is a function here. Right? This doesn't mean multiplication, right? It's a function notation. What is f of x plus h? If I know f of x is 2 minus x squared, what is f of x plus h?
Is it f of x plus some h value?
So you have 2 minus x squared plus h, and then minus minus 2 minus x squared all over h. It is not. But that's why I'm doing this. It's actually a very common error to do that. And by the way, interesting thing is if you do it this way, you'll always get 1 as the answer, no matter what the function looks like. Because if you have, say, a 2 minus x squared plus h minus a 2 minus x squared all over h, all of these guys would cancel. You would be left with h over h, and you'd always get 1. So sometimes it's funny, like I would like do like maybe a multiple choice exam or fill in the blank or something like that. And whenever a student fills in the blank with 1, I know what they did. So you did this, didn't you? Like, how did you know? Like, I didn't even show my work. Yeah, it's a very common mistake, and you'll always get 1 as the answer. So no, f of x plus h. So this is what I meant earlier, where you need to remember about composite functions. Remember guys that look like that, f of g of x, right? It's like your g of x is the x plus h, right? Now, what should you do when you see something like that? Right? So, now, for whatever reason, students tend to get it when I put numbers. So let's actually do a number. So that's your function. If I were to ask you, what is f of 1? What would you say?
You would substitute x with 1.
Right. Exactly. Right. And you would get what here? 0. Yeah. What if I said f of 2?
Four.
Yeah, but what did you do? How do you compute that?
You do 2 minus parentheses 2, close parentheses, minus 2 squared.
Okay, so you would get minus 4, yeah?
Yes, minus 4. Yeah.
Okay. What is f of x plus h? Look at what you did with the 1 and the 2. Now, if I replace that with x plus h, what would you do?
Substitute x with x plus h. So 2 minus parentheses x plus h, close parentheses, minus x plus h squared.
Exactly, right? Functions operate by the inputs. So when we see f of x equals 2 minus x squared, what you should be thinking is that this is just a rule where the x is operating as a placeholder, right? Where literally anything that goes in this position goes in the positions of x, right? X gets replaced by this. right? X is a placeholder. That's how function notation works. So when we say f of x plus h, what that means is everywhere you see x, everywhere, replace it with x plus h. And for heaven's sake, notice that I put that in parentheses. I haven't forgotten the lesson of this section, use parentheses. They're very, very important. By the way, that's another reason why this was incorrect, because we didn't have parentheses here. But we'll deal with that a little bit later. This is a very common problem type where students don't write parentheses and they're like, I knew it was there. And then they mess up and they don't get to simplify it properly. Right, so that is what f of x plus h means. So if I say f of x equals 2 minus x squared, it does not matter what I put in here. I could put f of smiley face and you would know what to do. You put a smiley face in parentheses and a smiley face in parentheses and square it. Whatever goes in here goes in these positions. That's what it means, right? And students usually get it right when I put numbers, but then I put x plus h and then everyone loses their minds, right? So yeah, don't remember the principles, right? There's a certain thing you do when you put something here. That thing does not change if it's a 1 versus a 2 versus an x plus h. It's the same principle. Whatever goes here goes here and here. Whatever goes here goes here and here. Whatever goes here goes here and here. There's a principle to it. It means something. Whatever goes in the parentheses on the left, it replaces every instance of x on the right, right? Okay, so let's start over. So our f of x is 2 minus x squared. So if I ask you about f of x plus h minus f of x all over h, what is that? What would I write now? What is f of x plus h? By the way, this guy here, I want you to note 2 minus x squared and plus h is actually equal to f of x plus h separately, where the parentheses is not including the h, right? So the location of the parentheses actually matters. It matters that the parentheses happened here versus here, right? And when you don't take parentheses seriously, like you get messed up by that. Okay, so right, f of x plus h, what does that mean? What would we get? Yeah, go.
It'd be 2 minus parentheses x plus h, close parentheses, minus parentheses x plus h, close parentheses squared, minus 2 minus parentheses x, close parentheses, minus x in parentheses squared over h.
Where's the parentheses?
Like parentheses x, close parentheses squared. For the, oh, and then like, would you put parentheses around like the, like after the minus?
You mean like this?
Yeah.
No?
Yeah, but like inside of the, like the square on the outside of it on the last term.
That's the same thing, right? So
Okay.
this and this are the same.
Okay. And then would you put parentheses over like the separate term, like like the,
So, I mean, here is you're subtracting f of x, right? So
Yeah.
you want this like that, right?
mhm.
So you want to open parentheses 2 minus x squared. You're subtracting f of x. When you subtract the sum of terms, the negative sign has to distribute. So you need parentheses. You need it here. You need it here. You need it here. Very, very important. And that's the first line, right? I can tell you from experience, half of students mess up on the first line. Sometimes even more than half, depending on the class, because they forget what it means to take composite function, what it means to say f of something. Right. But we made it. So now what? Oh, well, I see I can cancel the h here, yeah? Yeah? No, you can't do that. I kill you. Jhevon kills you if you do that. You cannot do that. Why? There's subtraction signs all over the place. You are canceling across the sum. Not allowed. Okay. So I can't do that. What can I do? Well, I have a bunch of parentheses. We know how to remove them, right? Hopefully, if I remove them, things can simplify. So let's distribute this. And that here, that's going to be x squared plus, well, the negative sign is going to distribute. Right? Everyone with me so far?
Wouldn't that x plus h squared be x squared plus xh plus h squared?
2xh. Okay, so I didn't fool John. The rest of you fail. Right? What did I just do? I just distributed a power across a sum. You didn't even notice I did it, right? That's what I'm trying to tell you. Like, you have to have these things at the forefront of your mind. I just did this mistake right here. Right? The x plus h, I turned it into x squared plus h squared. Not allowed, right? No. Distributed power across the sum. Not allowed. So half the students would have gotten the first line wrong. And then out of the ones who made it past the first line, a bunch of them are going to make this mistake. It's easy. They sneak up on you, right? That's the point of me doing this problem, to show you that if you're not careful, like when you're writing down a huge, like a long line of stuff, you're going to do this without even realizing it. That's why I had to use that inflammatory language. I call it blasphemy. Like, oh my God, don't do it. Like you should like be like, you know, you should be scared of doing it. So no, that's not correct. Right. So this would be a common error. This up here is also a common error. So the maybe I don't want to put that. Maybe I should put that over to the side. Common error is to do that, which is it's like it's not correct. Okay, let's keep the correct answer over here. Okay, so what we need to do is know that we cannot distribute powers across a sum. And so we first write out what that is. We know that a plus b all squared is a squared plus 2ab plus b squared, right? I want you to recognize that I kept the parentheses here. Because that negative sign out here has to be distributed, right? So now I can go in and do what I have to do. So that's 2 minus x minus h minus x squared minus 2xh minus h squared minus 2 plus x squared all over h. Oh, I can cancel the h's now, yeah? Cannot cancel, illegal. What can I do? I know I can't do that. What can we do here?
You can simplify the top line by adding the like terms.
Right, 2 minus 2. 2 kills the 2. The minus x kills the positive x. The minus x squared kills the positive x squared. And I have minus h minus 2xh minus h squared. And now I see my mistake. I should have canceled these h's right here. Yeah? No. I can't do that. What can I do? What's the correct next step?
You could factor the h out of the numerator.
Right, h is a common term. Right? Once you realize I can't do that, now you're looking for something else to do. You realize, oh, there's an h in everything. I can factor that out. And now you have a multiplication. Now we can cancel that h, finally. And that's your answer. Right? So except for like division by 0, this one problem has all the mistakes that I mentioned before combined into one. And I've seen every combination of those mistakes ever. Even after I warn people, I hey, watch out for this, watch out for that, watch out for that. They still, on the test, they do it all the time. I don't know. I don't know what. But yeah, that would be the correct solution. For practice, I want you to try this. Compute f of x plus h minus f of x over h for, I'm not going to do it, but I want you guys to practice. What if I had a radical x? How would that change things? What if I had 1 over x squared? Let's be a little bit kinder. 1 over x. Let's keep it easy. And then you can practice one a little bit similar. Try those. See if you can get to what the answer should be. Yeah. So those are the blasphemies, how students make mistakes, why they're important, and the fact that they sneak up on you, right? Sometimes you're working on a problem and it's like, you know better, but because there's so much stuff going on around you, you mess up. So you just want to make sure that you condition yourself. I never do this under no circumstance, right? Like when you cancel across a sum, you should feel like a stabbing pain in your heart, right? You just know, oh, I just did something wrong, right? It should get to the point where, like when, even if you don't remember all your English grammar rules, sometimes you can know when you said something that doesn't make sense. You feel like you said something wrong, right? Math should be the same way, right? When you write down something wrong, I feel like I missed a parentheses. Like, no, it's not they, it's them, right? Like math should be the same. And that comes from you just knowing the rules and really hammering it home. Like, I'm not allowed to do this, right? It's kind of like a subject-verb agreement. Like, I have to put parentheses here, right? You just need to know that. You're subtracting something, you open parentheses, right? It's just how you do things. Okay. All right. So that's a detour because very important that we went over that stuff. Because yeah, so when, like I said, when students are talking about, oh, calculus is so hard and blah, blah, blah. Nah, they fail calculus because of these reasons. They do things like this, like what I was showing you here, right? Because in calculus, I'm going to ask you to compute this guy all the time. Well, we're going to do a section in the book where you're going to have to be computing this often, right? And you're going to be like, oh, calculus is so hard. But it's like, that's not calculus. Like, that is algebra, right? You should have known how to do that a while ago, and try not to forget. Some of you probably took pre-calc a while ago, so you've forgotten, but you can't forget. You need to review all that. Okay. Continuing with the syllabus. So yeah, look out for those guys. Very common mistakes, but very avoidable also. All right, contact. Moving on to the next section. Very, very important. So you want to make sure that you receive contacts from me. I sent out a bunch of emails to you guys from like 5 different sources, and I'm going to verify later which source that you get, which sources you got. So you need to make sure you check your email and check that what you've received, and so you can know. But we'll do that a little bit over the break. But context is very important. We need the communication up. Don't let anything lapse. So make sure that you get emails from me, particularly from my email address, which it's jsmith306@fordham.edu, and Jupiter Grades or Jupiter Ed or whatever they're calling it now. Usually I would send mass emails through one of those 2 avenues, usually Jupiter. I really hate Blackboard. I'm never going to use Blackboard again. I did it now because I just wanted to try to reach out to you guys in every other avenue, but like, I'm not going to use Blackboard from now on. So yeah, make sure you got those. Feedback, very important. Highly encourage your feedback. Just make sure it's constructive. So don't just be like, your teaching sucks. Be like, your teaching sucks because you don't do this, you don't, right? So I am here to help you learn. So you need to tell me what's working and what's not working, and meet me in office hours. Speaking of help, there are many sources from which you can get help. Of course, first there's me. You can come to see me during office hours. You can reach out on Piazza. So you can have help from me. Also, the class webpage is going to be a lot of help. I highly recommend that you check the class webpage regularly, because like I said, there's a lot of resources there. I put old quizzes there, old tests are there, a lot of materials to practice. You have links to everything. You'll have links to the videos. You'll have links to the syllabus. You'd have links to the homework. You'd have links to everything you need. So always be looking out on the class webpage, which I posted that in the chat. So make sure that you got it. If anyone came in late and you didn't get that, I think someone did come in late. So let me repaste that link. So make sure you have that link to the class webpage. Okay. Other sources of help. Tutoring may be provided. I know in the spring, they had online tutoring offered by the math department and the dean's office, but I don't know if anything is set up for the summer yet. So I'll let you guys know about that. So that may be a thing, but I'm not sure. But there are a lot of other websites that are really nice. Wolfram Alpha, Lifesaver, Symbol Lab, Lifesaver. I use those guys myself all the time. You want to check that you're graphing something correctly, graph.tk can check, as well as Desmos. So these are some nice websites. You can probably, let's do I even know how to? How do you find the difference quotient? Shift. F of x. I don't use the keyboard here as often. Oh, this is going to be annoying. F of x equal to minus x minus x squared find, let's see if it's equal to f of x plus h minus f of x all over h. Oh, look at that. Right? So you can check your work. Like there are times when I don't even have to give you the answers to stuff. Like you can actually just check your work. So yeah, so give you something like this. So you get minus h minus 2x minus 1. Was that what we got? Yeah, minus 2x minus h minus 1, right? So that was the answer. So when you practice these guys, you can know what you should get, right? So if instead I said, to get square root, you can do SQRT, or you can just write x to the half power. And that's the answer you should get. This guy right here. The 1 over radical x plus h plus radical x. That's the simplified form. When it comes to the difference quotient, what you really want to do is you want to cancel that h in the denominator. You don't want an h there. We'll see why you don't want an h there, but you keep going until you cancel that h. Now you don't have that h hanging out. But yeah, you can check your work with Wolfram Alpha. So, right, and all these sites are really useful. Student disability services. If you have a disability that you think might affect your standing in the class, want to make sure that everyone has an equal opportunity to do well. So be sure to reach out to disability services ASAP. Yeah, usually class rules, pay attention, don't be on your phone. Engage more than you want to, more than you would in an in-person class. It's necessary. Like I said, have your cameras on, engage. You guys are pretty good with that as well. Academic integrity, the usual thing, don't cheat, don't cheat. It's surprisingly easy to tell if you do, so don't. Here are some important dates. You should consult the academic calendar, but the summer, there's not really a lot of stuff going on. There's not a lot of holidays or anything like that. But if you have, I believe tomorrow is the last day you can add or drop a class if you're taking several classes during the summer, which that would be crazy. Why would you? And if you have any incomplete grades from the spring, they will change into Fs by June 11th. So you might want to make up that work. The last day of class is June 24th. And then our final exam is July 1st. So those are some important dates there. And here's what we will be doing. So this is the plan. So we will be covering these topics. So from our textbook, we're going to do like chapter 1, chapter 2, a couple of sections of chapter 6, chapter 3, and chapter 4. So for your test 1, I thought I said chapter 3. Try to make sure you do all the homeworks up to these sections before test 1 happens, and practice all of those. So test 1 is going to cover the first 15 topics. And test 1 is going to be on June 11th, which is a Friday. But I'm going to sort of leave it open for like a 24-hour window. So hopefully at some point you'll be able to do it. And then test 2 is going to be on June 25th. And as mentioned here, the final is going to be on July 1st. So you have all that information now. And again, you can get this from the syllabus on the class webpage. All right. I think, yeah, we're finally through the syllabus. So one other thing I want you guys to do, we're going to take a break now. And aside from taking attendance, I do want to have you guys fill out something so I can make sure. So I put a link in the chat. It's to a Google form to just find out a little bit about the demographics of the class. Make sure that you're in the right place. Make sure that what sources did you get emails from me from? It'll have you answer questions about that. Yeah, so you can fill that out. And what I'm going to do now is I'm going to stop the recording so that I can call your names out.
The show will start in 9 minutes. The show will start in 8 minutes. The show will start in 7 minutes. The show will start in 6 minutes. The show will start in 5 minutes. The show will start in 4 minutes. The show will start in 3 minutes. The show will start in 2 minutes. The show will start in 1 minute. And now, on with the show.
Yay! Okay, we're back. Let us continue. All right. So, You guys are hearing me okay, right?
Yeah.
Okay, good. I switched my headphones because I think these were running out of battery. All right, so next order of business. We're going to do a crash review of exponentials and logarithms. So there are 6 main types of functions, and we're going to talk about these just generally in down the road. I don't know, probably by this weekend, maybe. But exponentials and logarithms are going to be particularly important. There are a lot of things I'm going to be deriving in the class using exponentials and logarithms, and there are a lot of techniques in calculus that depend on exponentials and logarithms, and students tend to not know about them as well as they should. So I want to spend some time going over them. I do also expect you to know about trig functions, but in Calc 1, we don't use trig functions as extensively. Those of you who are going to Calc 2, trig is coming back with a vengeance, right? Especially if you go through a traditional curriculum where you're doing things like polar coordinates and et cetera. But students are usually good with all the other functions enough, but they're not as good as they should be with exponentials and logarithms. And so I want to make sure that we can do that. So crash review, it's not meant to be comprehensive. It's just to remind you of some basic things, make sure that you know how to work with these different types, these 2 kinds of functions, because they're going to be very important. Okay, so let's begin. So, oh, am I right? We want to look at an expression like x raised to the a, right? Here, x is called the base, and a is called the exponent or power. Now, you guys might recall, if a is a positive integer, what x to the a means is that you take x and you multiply it by itself a times, right? But this can be generalized. It turns out it is mathematically consistent to do certain rules with these things. So this leads to the fact that this can be generalized leads to the laws of exponents. Okay, so it turns out that we can do various types of arithmetic with expressions like this, and they function in the following way. So, for example, if we have x to the a times x to the b, what do we get?
X to the a plus b.
You guys remember?
Someone said
X to the
a plus b.
plus b, right? You have a x's in a row, then b x's in a row. Together you have a plus b x's in a row, right? Just going by this principle here. Similarly, if we have x to the a divided by x to the b, we have x to the a minus b. Obviously, we have x to the 1 equals x, because you just have x multiplying by itself one time. A fourth rule, if you have x to the 0, this is 1. And you might wonder why that is. Well, that's because x to the 0, you can think of this as x to a number minus itself, which is just this by rule 2, which is 1, because you divide something by itself. And this happens by rule 2. Right? So it just makes sense for x to the 0 power to be 1. But since we're dividing, you want to notice that our x cannot be 0. Right? The reason why x to the 0 is 1 is because of this division, and we can't divide by 0. So x cannot be 0. 0 to the 0 is undefined, right? I should probably mention that. It's going to be a very important expression later on when we get to something called indeterminate forms. But we raise something that's not 0 to the 0 power, you will get 1. What else? If I have x to the a raised to the b, so if I have something to a power raised to another power, in this case, you multiply the powers. 6. Powers distribute across products. That's a rule that you should know. They distribute across divisions. That's something you should know. Right? Of course, y not equal 0. And if we have something to a negative power, do you remember what that means?
Is it 1 over x to the a?
It means 1 over that thing to the positive power. And again, x cannot be 0. And you might say, why is that? Well, if you have x to the minus a, that's the same as x to the 0 minus a. Well, that's the same as x to the 0 divided by x to the a, and by rule 2. And then x to the 0 is 1 by rule 4. You don't have to memorize them in order, but I just want you guys to know that these things aren't random. Like, there's a reason why all of these guys have to work out. But I'm assuming that your pre-calc or algebra teacher explained all of this, so I'm just really running through very quickly. There's a 9th rule that's going to be important to us. X to the a divided by b. Anyone remember what that is?
B square root x to the a.
Lizzie?
Yes.
Oh, hold on. Oh, go again?
B square root x to the a.
Right, the bth root of x to the a.
Yeah.
Right, which is, this is equal to, you can take the bth root and then raise to the a if your x is not negative, right? Because if it's negative, you have to worry about if the b is even or odd, and the a is even or odd, all sorts of stuff. Now, either way can work, so you should be aware. For example, if I have 9 to the 3 halves, you can think of this as 9 cubed raised to the half, or you can think of this as 9 to the half raised to the cube. And one is easier than the other, right? So you can think of this as that, or you can think of this as that. And clearly this one is easier. So that's just going to be 3 cubed, which is 27, right? So you can mix and match the radical and the power, and you can move them. You can do one versus the other. And this really works because of the multiplication rule over here. Because I can think of the 3/2 as 3 times a half, or I can think of it as a half times 3. And one way versus the other should be the same thing. Okay, so that's that. There's a mnemonic for remembering this. If you didn't remember, it's called flower power. So when you have x to a over b, you look at the power and it reminds you of a flower. The bottom is the root. The top is the power, which rhymes with flower. So this means a is the power, b is the root. So that leaves you with the bth root of x to the 8th power. Right, so you can remember that, flower power. Nice. Okay, so those are the laws of exponents, as they're called. These guys can be simplified in the following ways under these rules and conditions. Okay, so we should know that, right? So you take like x squared times x cubed, the answer is x to the 5th, right? You take x cubed divided by x to the 5th, the answer is going to be x to the -2, or 1 over x squared, if you want to think of it that way. Being able to jump between these guys is going to be very important for what we will be doing later. So it's very important that you remember all these rules. Now, the next thing I want to talk about, exponential functions. And the quintessential form. It's a function that looks like y equals a to the x, where a greater than 0 is a constant. And of course, so example, y equals 2 to the x, y equals 1/2 to the x, y equals pi to the x. These are all what we call exponential functions. X is the variable. It's the guy that you're plugging in, right? And of course, we can do transformations. So that's something like you can multiply this by something else, maybe add something else. So something like example, y equals 2 times 3 to the x plus 4. We still think of this as an exponential function. It's just moved around, shifted and stretched and stuff like that. And you should remember, I do expect you to remember about transformations of functions. Did I list that? Like when you add a number to a function, what happens? Maybe I should put that in. Right, when you multiply a function by a number, what happens? Blah, 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 etc. Right, so, but the basic form of an exponential function is the base is a constant, the power is a variable. It's very different from if the base is a variable and the power is a constant. That's called a power function, and polynomials are examples of those guys. But we'll talk about that in a little bit. So this is called an exponential function. What I want you to know about exponential functions is these functions obey the laws of exponents. So for example, if we have f of x equals 2 to the x, and I have g of x equals 3 to the x, then if I were to multiply these two functions, this is 2 to the x times 3 to the x. I can think of this as 2 times 3 to the x. It's the same as 6 to the x, right? So they would obey the laws of exponents, everything that we discussed before. So powers can distribute across products. The same thing is going to happen. Another thing you need to know about is the graphs. So here, assume a is greater than 0, but also a is greater than 1. And as we'll see, we do not need to worry about between 0 and 1. So we always want the base to be positive, and that's because if your x hits like a half or something, you take a square root, and if your a is negative, you'll get complex numbers. So we want to keep it positive all the time. But when it comes to graph, you only need to remember the graphs for when it's greater than 1 specifically. So equals to 1 doesn't make any sense because 1 to the x is just 1. It's not very interesting. It's a constant function. But if your a is greater than 1, then the graph of an exponential function is going to look like the following. Right? Asymptotically, we'll approach the x-axis going that way, and y, x. That's how an exponential function would behave. Notice that as x goes to negative infinity, your y value will get closer to 0. And as x goes to positive infinity, your y value will go to positive infinity. But we can do transformations. So for example, I can also look at y equals minus a to the x. And you should know what that does. It flips a graph upside down. So that graph would look like this. And what you could also do is you could have a negative in the power, right? When you turn an x negative, what does that do? So when you turn the y value negative, it flips in the horizontal. When you turn the x negative, it flips in the vertical. So this one is actually going to look like that. And of course, you can do both. So you have y equals minus a to the minus x. And that one is going to look like, you're going to flip in the horizontal and then flip in the vertical. That one's going to look like this. Now, this guy, if I look at this one over here, so for example, what if I had a equals a half, right? Do I need to know what the graph of that would look like? Well, if I let my y equals the a is a half to the x, by the laws of exponents, this is 2 to the minus 1 to the x. But then that is just 2 to the minus x, right? So if your a is between 0 and 1, the only thing it does is equivalent to putting a negative in the power. Then y equals a to the x is just the same as 1 over a to the minus x. And so a negative in the power will invert the base. So once I know how it works for things that are bigger than 1, I know how it's going to work for things that are between 0 and 1. So for example, I know that y equals 2 to the x is going to look like that versus y equals 1/2 to the x. It's going to look like this because that's the same as 2 to the minus x. So those are the graphs. And again, I assume you guys have seen these before. I'm just running through to remind you of these things. One thing you do want to know, though, is there really a difference between the base being positive, base being a constant versus the power being the constant? So if you look at y equals a to the x versus y equals x to the a, where a is the constant. So this guy is known as an exponential function. while this guy is known as a power function. And if your a is a non-negative integer, that gives you something that we call a polynomial. So for example, if a is 2, you get x squared. That's a polynomial that we call a quadratic. Its graph looks like a parabola. Okay. How do these two functions compare to each other? So let's compare something like y equals 2 to the x versus y equals x squared, right? The fact that the power is the 2 versus the base is the 2, does that really make a difference? So graph these on the same axes. You see, when you do that, it might not seem like they're very different. So for example, you can be like, all right, yeah, so x squared is going to be like that. You know, that's my y equals x squared. All right, what is my y equals, or maybe I feel like I want the other one read. So that's my y equals x squared, and my, come on, iPad. Get an iPad, they said. It'll be fun, they said. And you'd have your y equals 2 to the x. And this is what they call expectation versus reality, right? So expectation, a lot of students will draw these on the same, and it's like, not much different. All right, they're kind of the same. One curves that way, the other one curves both up. You know, they're kind of the same thing, right? They're just two curves. It's nice. Look, they're playing together. You know, they're sticking by each other. You know, they're friends forever, best friends for life, ride or die. All right. However, the reality is they are very different. How so? What do you mean, Jhevon? How are they different? So let's increase the scale. So suppose I zoom out. So over here, it's like a gajillion, bajillion, gazillion, right? So your x is going off to infinity, right? Like it's a huge x, right? So now my 2 to the x, we know what that would look like. It's going to look like so here, zoom out. What do you think the x squared is going to look like? Like the U shape, yeah? Like you zoom out very, very far. So it's going to be like a U. And the truth is, it's not, right? If you zoom out and you get x huge, here's what the x squared would look like. might as well be 0. 2 to the x is going to outgrow x squared so much that x squared might as well not even try. Might as well be 0. It's not close. Exponentials grow much faster than power functions. So if i.e. if a is greater than 1, then if I have a to the x versus x to the b, then your a to the x is going to be much bigger than this guy as x goes off to infinity, no matter what b is. So if I just have like 1.1 to the x versus x to the eventually, this guy outgrows the other guy. This will eventually be huge compared to that. So much so that the x to the blah, blah, blah may as well be 0. It's not a drop in the bucket, right? It's kind of like, all right, let's take Jhevon's net worth and compare it to Bill Gates' net worth. Dude, might as well I have $0. It's literally not, what is the comparison here? Like, it's not close, like at all. Like, myself and someone with $0 net worth are the same compared to Bill Gates. We're like nothing, like it's not even close, right? So it's like one can get so huge that it completely dwarfs the other one. And that's a very, very important thing. Exponentials, increasing exponentials will outgrow any increasing power function, no matter how huge the power is. That's going to be very important come later. So I just wanted to point that out. They are not the same. We are not alike. On some scale, you might think they're comparable. They're not comparable. They're not the same thing. The 2 to the x is going to beat x squared. In fact, 2 to the x will beat x to any power. X to the billion, yeah, it'll put up a fight for a little while, but eventually 2 to the x is going to outgrow x to the billion. Exponentials outgrow power functions by a lot. So much so that eventually, for large x, the power functions may as well, they're effectively 0. They're nothing. They might as well not even wake up in the morning. So that's one thing you want to know. We'll expand on that relationship later. I'll give you some more. How functions relate to each other is going to be very important for us to know. For now, just know any increasing exponential will beat any increasing power function. As x gets large. So we're going to be doing things like letting x approach infinity, and we'll talk about what that means pretty soon. But when that happens, you need to know if there are two functions competing, one's going to win, and it's not going to be close, right? That's going to help us solve a lot of problems. Yeah. Now, there is an important exponential function. There happens to be a very special exponential function, an exponential function that stands head and shoulders above the rest. Does anyone know what that function is? That function is y equals, wait for it, e to the x, right? This guy is called the natural exponential. It is the most important exponential function. Now we are going to see some ways in which this guy is important, but Calculus 1 will not do this function justice. This function is actually super important. There are, in fact, some people would go as far as to say it's not just the most important exponential function, it's the most important function in general. Like this function is so helpful, it's not even funny. And it's an exponential function, which means even though I wrote a letter E, E is actually a number. E is a constant. You know, like pi, right? When I write the Greek letter pi, it actually represents something. So E is roughly 2.71828 non-repeating decimal. Just like how pi is 3.1415926, blah, 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 right? It represents a number when you write E. It is named after the Swiss mathematician Euler. Pronounce Euler. Your biology friends are probably going to call this Euler. They don't know what they're talking about. His name is pronounced Euler. He's Swiss, right? This guy, very prolific mathematician. This guy was cranking out theorems even into his old age, which is actually very rare. Back in the day, mathematics was a young man's game. All these crazy math theorems that we're using today were invented by like teenagers and people in their early 20s and stuff like that. Like usually if a mathematician gets old, they usually didn't contribute as much. It's kind of flipping to the opposite these days because there's just so much knowledge. By the time you get knowledge to give anything new to the field, you're always ready going to be like super old. But back in the day when we're just discovering stuff, it's all the young people who were discovering stuff. Euler was an exception. He was like prolific throughout his entire life, pretty much. Even as he was going blind, he was still like kill in math, right? So what he was studying this problem. So remember when compound interest. If we have A equals P times 1 plus R over N to the NT, we say right, P was your initial principal. R was your interest rate. N is the number of times compounded per year. And T is the number of years. T is the variable, which means this is an exponential function. So compounded money grows like that, right? And again, in the short term, you might not really notice what's happening, right? So in the short term, even if your money is growing by compound interest, you're not going to really notice much difference between that and just a checking account where your money, you're just putting in the same amount of money every day, and your account is like growing like a straight line, versus you're in a savings account with a high interest rate and it's being compounded. Your money doesn't grow like a straight line, it grows like this. And you might realize that, you know, after a few months, a year, it's like, oh, you got a couple extra dollars here, a couple extra dollars there. No big deal. It's not the same. Turns out it's very different from that. And it's one of the reasons why Bill Gates is as rich as Bill Gates, because Bill Gates's money grows like an exponential function. Everyone else's money grows like a power function, right? Eventually, it builds on itself. So it's like, yeah, you're not going to notice in 1 year, but in 20 years, 30 years, 40 years, there's going to be a huge difference. If you save $500 a month in the stock market growing at 8%, in 40 years, you're a millionaire, versus the guy who saves $500 a month under his mattress for 40 years, he's still going to be a thousandaire. It's not going to be close, right? So this thing grows super fast, and you might not notice it in the beginning. And another thing you want to know is that there are certain types of debt that grows compounded. So they grow like an exponential function. For example, credit card debt. So you might think paying your minimum credit card on your credit card is not that big a deal. Oh, you know, I can get away with paying $30 extra here. You know, it's not, oh, my interest, added interest was like $20. Oh, that's fine. You know, I can put that, paying that off. You know how people get in trouble with credit card debt? It's because they think their debt is linear, but it's compounded. Eventually, it grows out of hand, right? And credit cards, they compound every day. And the average credit card interest rate is like 20%. And it gets out of hand really quick if you're not paying attention. Well, not really quick. You're not going to notice right away. But eventually, if you keep putting it off, you're going to get in trouble. you cannot keep up with those payments, and that's why they compound the interest. So now Euler considered this situation. What if we really wanted to be evil, right? And really put people into debt, right? So Euler considered an interest rate of, forget 20%, let's make it 100%. Like, we really want to put them in debt. And n goes off to infinity. Don't compound it every day. Compound it an infinite number of times every day, right? And then he studied the question, what would happen to $1 compound like this in 1 year? Now, because people know how exponential functions grow, they're like, oh man, you're gonna be like infinitely rich. You're gonna have like a huge sum of money. That's crazy, man, right? 100% interest rate compounded infinite number of times. You're gonna be a millionaire in 1 year. Come on. Turns out the answer is no. Turns out balance would be just under $3, $2.72. It turns out that this number is what he called E. You'd have E dollars. So it came from compound interest, and it turns out that that in particular makes it a very useful number. So that's where the number came from. So like a lot of people, we developed the number pi. It came from a circle. Turns out the number E comes from compound interest, and Euler was the guy that discovers it. That's why it's called E for Euler. So it's a very, very important function, and that's how it was birthed a long time ago. So that's E, right? It's just a number, and e to the x, y equals e to the x, is a very, very important exponential function. The most important exponential function, the most important function in calculus in general, and we'll see a little bit of why that is. Yeah, so that was just an interesting tangent there. Now on to the other one, logarithms. Logs for short. So we dealt with exponentials. Now we're going to deal with logarithms, right? And we're going to talk about logarithmic functions and what we need to know about them. So let's go to definition. The logarithm of a number to a given base is the power to which the base must be raised to get the number. Now that understandably sounds very confusing, but a logarithm is a power. It's an exponent. So they're actually intimately connected to exponentials, right? But they're kind of like if you looked at an exponential the other way. So let's start to write this down in more mathy language. What I'm saying is the logarithm of a number to a given base is equal to the power. What power? It's the power that you need to raise the base to get the number. In symbols, this is how it looks. And this leads to Maybe I should. In symbols, this is how it would look. If I have a log to the base a of b equals c, what that means is a raised to the power c will give me b, right? So a logarithm is just another way to think of like an exponential equation. The logarithm is when you want to solve for the power, right? The logarithm is the power, right? Okay, now that's going to be important soon. This leads to the laws of logarithms. Law 1. It's actually the definition. You must know this. Log to the base a of b equals c is the same as saying a raised to the c equals b. So, example, I know that log to the base 2 of 8 is, what is log to the base 2 of 8 based on this definition? It's the power we need to raise 2 to in order to get 8, right? So if I say log to the base 2 of 8, what is that?
3.
It's 3, right? That's basically what I'm saying. Why? Because 2 raised to the 3 would give me 8. That's why, right? So it's just, you're just thinking of 2 cubed equals 8 in a different way, right? Where you want to take the 3 and you want to put it on one side of the equal sign by itself. What's on the other side is going to be a logarithm. And it turns out that this is actually surprisingly useful. Now, I know a lot of you are happy. A lot of you are just like, I'm happy with this. Why do we need to make this so complicated? What's wrong with math people making things complicated? We're not. It's actually making things a lot easier. In fact, logarithms save lives. They were invented to assist with nautical navigation, and they literally saved lives because they made navigation calculations easier. So let's look at some ways in which it made things easier. It turns out logarithms can turn powers into products. So if I have log to the base a of something raised to a power, that's the same as the power. I can move the power down and put it in front. So example, if I have log to the base 3 of x to the 5th, it's actually the same as me writing 5 log to the base 3 of x. Right? I can take a power and move it down and turn it into a product. So I go from raising something to a power to multiplication. It knocks it down an operation. Law 3. Logs turn products into sums. So if I have a log of x times y, it's the same as log x plus log y. So example, if I have log to the base 3 of 2x, that's the same as log to the base 3 of 2 plus log to the base 3 of x. I can turn a multiplication of 2x into a sum where the 2 is separated from the x. So logs can turn products into sums. Logs can turn division into subtraction. So example, if I have log to the base 2 of 3 over x, this is the same as log to the base 2 of 3 minus log to the base 2 of x. I can go from a division to a subtraction. Now, hopefully you appreciate the connection here. Remember with exponents, when you raise something to another power, you multiply the powers, right? So that's multiplication. If you take one thing to a power and you multiply the same base, you add the powers. If you divide things of the same base, you subtract the powers. There's a connection here between the exponents and the logarithms. Hopefully you're appreciating that, but I'm not going to dwell on it too much. Another important law is the change of base formula. As it's called. This is a formula that allows us to change the base of a logarithm. This says, if I have log to the base a of b, I can rewrite this as log to the base c of b divided by log to the base c of a, where c is a convenient base. Spoiler alert, e is going to be a convenient base in the future. So if I have a logarithm that doesn't have base e, it will be beneficial to us to convert it to base e, and we can do so by using this formula. Here's a little simpler example though. What if I were to ask you, what is log to the base 4 of 8? In other words, what power do I have to raise 4 to in order to get 8, right? So if this is x, this means I want 4 to the x gives me 8. What is x? Well, if x were 1, 4 to the 1 is 4, all right? Bump it up to 2. 4 squared is 16. I overshot. Okay, so the answer has to be between 1 and 2. But is it exactly between 1 and 2? Is it halfway, or is it like more to one side than the other side? Like, how do you know? Like, can you think of a number that if I raise 4 to it, 4 raised to that number will give me 8? It turns out thinking of 8 in base 4 isn't convenient. But there's another convenient base, right? Where I can think of 4 and 8 in terms of that base. That would be nice. So 4 is inconvenient here. Uh, 2 would be nicer, right? Why is 2 nicer? Because I know what 4 is in base 2. I also know what 8 is in base 2. So what I can do is I can introduce a more convenient base. So by change of base formula, what I can do is base 4 is confusing. So what I can do is I can introduce a base 2, and I can introduce it in this way. That's just applying the change of base formula. And now what you'll realize is the answer kind of falls in your lap, because I know what log to the base 2 of 8 is, right? It's 3. I also know what log to the base 2 of 4 is. It's 2, because I have to raise 2 to the power 2 to get 4. So it turns out it's 3 over 2. So that's the answer. It's actually halfway. It's 1.5. It's not always halfway, but in this case, it just happens to be halfway. And don't believe me, you can check. We know how to do flower power now, right? So if I do that, this is the same as the square root of 4 cubed. That's 2 cubed. That's 8. Yeah, 4 to the 3 over 2 does give me 8, right? And I could figure that out using the change of base formula, right? So that's, it's more than a little party trick. We really care about it to convert things to base E, because like I said, E is very, very important. Some more rules. or more laws. So these 5 laws are, you have to know them, like no escape. You must memorize the first 5. The following, I would say it's optional to memorize, but I would also say it's highly recommended. By the way, the remaining laws that I want to tell you about, they show up pretty often. So it turns out that if you're studying enough, you'll end up memorizing them without even trying. So if you want to know, are you studying logarithms properly, or did you study enough? Do I really understand logarithms now? If you can remember the following rules I'm about to tell you, then chances are, yeah, as long as you can also apply them correctly. So law 6. Log of 1. So remember, the log to a given base of the power I need to raise a base to get the number. What do I need to raise a to in order to get 1 if a is a positive number? A to the what gives me 1?
0.
0. Right? So you see why it's optional? Because if I really understood this rule, then that's kind of obvious. Like if you think about it, like this, if this is true, then that had to be 0. A to the 0 would give me 1. If my b is equal to 1, that c must be 0, right? If it needs to work for any a, right? So you can even think of that by the definition, but it's just nice to know log of 1 is always 0, no matter what the base is. What about log of 0? A is a positive number. What do I have to raise it to in order to get 0? Turns out if you think about it, you'll realize the answer is undefined. There is no power you can raise a positive number to get 0, right? If you take a positive number to a positive power, it stays positive. If you take a positive number to a negative power, you just get 1 over the positive number to the positive power. If you take the positive number to 0, you get 1. There's no number you can plug in to make it 0. If the base is not 0, it'll never be 0. So it turns out log of 0 is undefined. In fact, log to the base a of x is undefined if x is less than or equal to 0. Because if you have a positive number, there is no power you can raise it to in order to make it into a negative number. So that's law 7. Law 8. Now, this one is going to be I'll give you the more straightforward one first. Log to the base a of a to the x. And so now the question is, what power do I have to raise a to in order to get a to the x? X, right? A to the x gives me a to the x, right? So if you log something if you log an exponential and the bases are the same, they kind of cancel each other. So that's something that you should know. So if I like log to the base 2 of 2 to the 5, well, that's just 5, right? The base if the base and of the exponential and the logarithm are the same, they kind of cancel each other and leave you with the input. And again, if you think about the definition, that's obvious. The last one, this next one, is a little less obvious, but it's true. The other way around works as well. If I take an exponential and I plug in a logarithm into its power, and the base of the exponential and the base of the logarithm are the same, they're both a, it turns out they also cancel and give you x. So, example, if I have 2 raised to the log to the base 2 of 5, that is also 5. Right? What I just showed you is that if you plug in an exponential into a logarithm, they give you the original input. And if you plug a logarithm into an exponential, it gives you the original input. Do we know what that means in terms of functions? When you plug one function into the other and it gives you the original x value back, and you can do this in both ways, what does that mean? What can you say about the functions?
Are they inverses of each other?
They're inverses of each other. So law 8 and law 9 show that if I were to look at a logarithmic function and an exponential function where the bases are the same, they are inverses of each other. Now, this gives you a lot of nice things. For one, it gives us an algebraic way to cancel exponentials and logarithms, right? So if I want to get rid of a logarithm, I know I can use an exponential. If I want to get rid of an exponential, I can use a logarithm. They're inverses of each other. It's kind of like if you want to solve an equation and you have like a +2 and you don't want the +2, you can subtract 2 because the negative is the inverse of the positive, right? If I'm dividing by 2, I can multiply both sides by 2 because the multiplication is the inverse of division. So I can manipulate equations and move things to another side by applying the inverse operation. So that kind of tells you that you can use logarithms and exponentials in that way. So this means, one, we can use logs to cancel exponentials. And use exponentials to cancel logs. Kind of like how you can use a subtraction to cancel an addition, or you can use a multiplication to cancel division. And two, we immediately get the graph because we know how the graphs of inverses behave. So if I know that my a to the x looks like this, it means I now automatically know what a logarithmic graph looks like. Because to get the graph of an inverse, you reflect in the line y equals x. So it turns out the logarithm is going to look like that. It's going to be a mirror image. And so now I know all the graphs for logarithms. So this tells you a greater than 1, then your y equals log to the base a of x. Looks like that. It passes through 1 because we know log of 1 is 0. If I have y equals minus log to the base a of x, I know what that does. It flips it upside down. If I get log to the base a of minus x, remember logs cannot take negatives. So in order for this to work, all my x values need to be negative so that the negative negative of the negative makes it positive, and then that will work. So it just goes on the negative side, passing through -1. And of course, we can do both. And that would give you this. Which, by the way, I'm not sure if I remember to say that, but for the exponentials, that's also true. When x is 0, that passes through 1. And that's how I know that the log had to also pass through 1. Because when x is 0, a to the 0 gives me 1. So the y-intercept is 1. And one more thing I want to mention here. Law 10. Now, this isn't really a law. It's more like me introducing notation. Log to the base e. Henceforth and forevermore for this class, when we want the base e, we call it ln. Some people call it ln. It's called the natural log, because e to the x is a natural exponential. This guy's called a natural log. It's the most important logarithm, obviously. If I just have log and no base, it means log to the base 10. Otherwise, the base needs to be specified. Note, ln x is just a usual log algebraically. I know the symbols scare people sometimes, but don't let it scare you. It functions like a logarithm, like any other logarithm. So it obeys all the log rules. It's just that the base, is e. So it means that ln of x equals y means that e to the y equals x, because there's an invisible e right here. So that's from law 1. Or I know if I have ln of x times y, it still becomes a sum, right? Etc. Right? So don't let it scare you. It's just a regular log. It's just that the base is e. Okay. To add to it, it turns out that logarithms grow slower than power functions. So that's the relationship. As x goes to infinity, functions on the right far exceeds functions on the left. So exponentials grow much faster than power functions, and power functions grow much faster than logarithms. How fast? Well, if you compare a logarithm to a power function, eventually the logarithm might as well be 0. It's not even trying. And then if you compare the power function to an exponential, eventually the power function might as well be 0. It's not even trying, right? So guys to the right are huge compared to guys to the left as x goes to infinity, right? And knowing how these functions relate should, it's going to be important. Now, I will stop here, but I am going to leave some things for you guys to try. for tomorrow, and we'll do this tomorrow, but I'm just going to copy them. So to make sure you understand the rules that I've been mentioning, I want you to try your hand at these problems right here. Everything you need to know to solve these problems, I've told you about, but I want you to try and apply it. So you're going to simplify these guys, solve a bunch of equations based on the rules that I told you. So yeah, lots of examples, but it's actually very important that you know how to work with exponentials and logarithms very well. I will also send you guys, in fact, let me do it now. I know we're over time, but I want to make sure that you have it right away. I'll give you guys a link to the notebook, to the notes that I have right now, even though it's going to be posted in a little bit. So I'm going to paste it in the chat. So those are the lecture notes. So it updates in real time as I'm writing. Maybe in the future, what I might do, just like I wrote these examples ahead of time, I might even write out some notes ahead of time so you guys can like bring the notes with you and you don't have to write as much and you can focus on understanding as opposed to writing. But try these. We're going to go through them very quickly next class. So the first half of next class is just to get through these guys. And then we'll actually start calculus. So we're not in calculus yet. This is still a review. These are problems that I would expect you to know how to solve since pre-calc, but I understand that that might have been a long time ago for some of you. So just quickly run through a review and I'll leave you guys with some practice problems. And we'll pick up there tomorrow. Yeah. Okay, so that's it. Thank you for your time and attention. I will see you guys tomorrow. Same place, same bad channel. Yeah, try those problems. You have the link to the notes, and that is it. I will bid you all a good night. And if you didn't receive communications from one or several of the things that I asked about in the questionnaire, you should probably email me and tell me, oh, I didn't get this email, or I didn't get this, or, oh, I got something from Blackboard, but I didn't get it from this place, or I got something from here, but I didn't get it from there. Let me know what lines of communications you guys are receiving. Or you can just shoot me an email and let me know that. All right. Good night. It's been a long night. Thank you for paying attention. I will let you guys go. So until then, I'll see you guys in the next one. Ciao.